1965. And it was the way that everybody thought that all planetary systems should and would look like this. So here, the relative sizes here are to scale, but not the distances. So here, closest to the sun, we have 4 small rocky planets here enlarged in this inset. And then further out, you have giant planets consisting of gas and ices. But they also contain a solid core. Now, the innermost planet, Mercury, that orbital period is about 3 months, while it's 165 years for Neptune. And it's 12 years for Jupiter. And this was a type of planet that they expected to find, a Jupiter-like planet with an orbit of 12 years. So it would take at least a decade to detect it. But they detected it immediately because it had an orbital period of 4 days, so it would be around here. So again, this was a way that we thought all planet system would look like. Also because we only had one system, but also because theoretical planet formation theories could explain very well this system architecture. Because planets form in a disk of gas and dust grains. And in this disk, it's very hot close to the star, right? So there's not so much solid material there. Most material is a form of gas very close to the star. But as you go further and further out, it gets colder and colder. And at some point here, the temperature has decreased enough so that water, which is very abundant, suddenly can condense. So you have like a snowstorm here. And these particles will be used to incorporate and build up planet cores. Massive planet cores that are needed to attract a lot of gas by gravity to form these giant planets outside, far away from the star. So there's not enough material close to the star to form Jupiters. That's why everybody knew giant planets cannot be close to the stars. But still, they discovered such a planet. So what was wrong? Well, the theoretical models weren't wrong. They were just incomplete. And the missing part was migration. Because planets don't form exactly at the same place where they end up. So all the particles in a disk, small particles up to massive giant planets, they affect each other via gravitation. And also, while there's still a gas disk, it's gas drag in the disk. So planets can move inwards. They can also move outwards. Sometimes they are kicked entirely out of the system. But this was shown rather quickly after the first detection. So we theoretically model how these planets could form. So how did they do this? What is the method by which they detect the first planets? How can they overcome all these difficulties? Well, they actually did not observe the planet. You remember the pale blue dot? That's a picture on Earth from home. It's here in our own planet system. We are trying to detect planets extremely, extremely far away. So that pale blue dot is much, much better than anything we can do for exoplanets right now. So what they did is they observed the star, the host star of the planet. And this is called the radio velocity method, RV method. And it has to date discovered more than 1,000 planets. And what it does is that it measures the movements of the star. It measures the velocity of the star, the velocity in the sightline of the star. And it takes advantage of the fact that, as shown here in the movie, the star and planets, both are moving around their common center of mass. So both are moving, but since the star is much more massive, it just moves a little. It's like it's wobbling back and forth. While the planet has a much wider orbit. So this wobble, this velocity, change in velocity in our line of sight, can be measured via the Doppler shift of spectral lines coming from the star. So we're actually taking a spectrum of the star at one point. And then a little later, we take another measurement and then another. So we take spectral line measurements as a function of time. And then we can get something like this. So this is an observed spectrum, and this is actually the first detected rocky exoplanet, Queloz 7b. And what you see here is each dot here is a measurement of the line of sight velocity of the star. You see here y-axis, radial velocity. And on the x-axis is time. So this is simply moving, a star moving towards us, away from us. Towards us, away from us. And then we can get the orbital period of the planet from this. This is one orbital period. And then we can get the mass of the planet relative to the star from the amplitude, because the star will wobble more if the planet is more massive, and wobble also more if the planet is close to the star. But, you know, it's very difficult to measure these tiny velocity changes of the stars. So, for instance, Earth makes the sun move, and the amplitude of that is only 10 meters per second with an orbital period of a year. This is extremely hard to measure. But Jupiter, on the other hand, that amplitude is much larger. It's 12 meters per second, but the orbital period is 12 years, so we have to observe for a long time. And this is hard. We researchers, we live on publishing articles. And it's very hard to observe something like 10 years, 20 years, 30 years, and then publish one paper. So that's why we are very fortunate that nature gave us these super short orbital period planets. Because if we hadn't detected that first one, we might never have detected any exoplanet at all. So anyway, so this method requires extremely stable, sensitive, and high resolution spectrometers. But there are other methods. There are actually many methods, but there are only two methods that have been the most successful, and this is one of them. But the most successful method so far is the transit photometry method. And that method measures the light from the star. And you can do that if the planet's orbital plane is exactly in our line of sight. If they happen to cross the stellar disk. You can see here in this animation that if they cross, the stellar light is here, and when the planet passes in front of it, a tiny bit of the stellar light will be removed. The planet will cast a shadow on the star. So in this way, we get the planet size and orbital parameters. So from the other RV method, we get the mass, and from this method, we get the radius. Combine the two, and we have the density. So here's actual data, also Queloz planet. This is a rather large planet, a Jupiter-sized planet. So here, you see these wiggles here. It's actually changes in light from the star itself. It's not exactly the same all the time. But these narrow dips here is from a planet that is transiting, passing in front of the stellar disk. Then you can get the orbital period just between two of these dips. And you get the size from the depth of the dip relative to the star. So it's a fairly easy method to understand, but of course in reality it is very difficult to perform. Even if every star has planets, which it seems to be, very few of them will have planets that are orbiting directly in the plane in our line of sight, right? Very few of them that will have that. So we may have to look at 100 stars or 1,000 stars, the light from many, many stars as a function of time before we find one, even if all of them have planets. And it's also very sensitive to very close-in planets, you will see later. It's very difficult to detect planets at the same distance as Earth or even Jupiter, It's very difficult. And the signals are very weak. Small planets like Earth passing in front of the sun removes only 0.01% of the stellar light. You also need continuous observation. Earth is passing, if someone is looking at us in our sight line, Earth will transit the sun once a year, and the transit only takes 13 hours. So you really have to look all the time. We are looking at a lot of stars. We don't know where the planets are. So we cannot look away, because if we do, maybe planets would transit when we look away. So it's best done from space, since we cannot observe continuously from ground. And large planets are, of course, much easier to detect than small planets. And also short orbital periods are much easier to detect. So as a comparison, the area of Jupiter is much, much larger than Earth. And the mass of Jupiter is more than 300 times more massive than Earth. So this is an actual image. Venus is transiting the sun, as seen from, it's from a space mission. It's Venus transiting in front of the sun. So if you have small planets transiting solar-like stars or large stars, the signals are very, very weak. So you really have to have ultra-sensitive instruments on board space missions to detect them. But if the same planet would transit a much smaller star, the signal will increase. Oops, this is really not like this. So here is the same size of the planet transiting in front of a much smaller star. So the stars can be about 10% in size of this, our sun's size. So this has become very popular to search for planets orbiting small stars. But as I will talk about later, these stars may not be good for life, for habitability. Anyway, so space missions are absolutely crucial for this field. So in this figure here, you have space missions on the top that are dedicated to exoplanet research. At the bottom here, you have other missions, space missions that are not dedicated but have done a lot of exoplanet research anyway. I'm sure you've heard about Hubble, Gaia, that are measuring the exact locations and distances to billions of stars in our galaxy. James Webb Space Telescope, that are doing a lot of observations of exoplanet atmospheres. And the Roman telescope that will do a lot of research, but in part it will use a completely different method. It will search for exoplanet via gravitational microlensing and has the potential to discover thousands of planets. But it has not been launched yet. But anyway, top here, dedicated to exoplanets. We had the first one. It was Corot. It was a European space mission that made several important discoveries. Among one of them was the first rocky exoplanet. But what transformed the field again was NASA's Kepler Space Telescope. And I will come back to you shortly why it transformed the field. But the difficulties with Kepler, actually Kepler have discovered most of all planets that we know today. But the difficulties with Kepler, that is stared at a small part of the sky for several years. And there were hundreds of thousands of stars in that field. So it stared on that field for several years. But, as you know, most stars are small. They are very, very far away. So most stars are very faint. So what we want to do is we want to detect them in transits. And then we want to combine that with radio velocity measurements to get the mass. And also to confirm that it really was a planet. But the radio velocity measurements require bright stars. And most stars in Kepler's small field of view were very faint. So for most of the Kepler planets, we have only measured sizes. We can never get the masses for these planets. But we want to do that. We want to investigate these planets more. We want to know what they are made of. Are they gas planets? Are they water planets? Are they iron planets, Earth-like or what? But we need both radii and mass for that. So that's why all new, the next generation space telescope. They all target bright stars with different solutions to the observing strategy, because the bright stars are few and scattered across the sky. So the first one was TESS, NASA's TESS, launched in 2018. Now TESS performs an all-sky survey. It observes everything. Perfect. We get all the bright stars. But that is for the expense of observing only, it observes every part of the sky for only about a month. And then it moves on to the next part. Otherwise, it can't cover the entire sky. So TESS mainly observes very short orbital period planets, like a few days or a week. 10 days is a long period planet for being TESS. Then we have a triplet in space missions from Europe. We have Cheops, Plato, and Ariel. Cheops was launched 2019. Actually, Didier, who discovered the first planet, was a scientific leader of this mission. Cheops is a follow-up mission. It doesn't search for new planets, so it observes one star at a time and can point anywhere to obtain better measurements, to get better size measurements. But what we all are waiting for, with a launch end of next year, is the European Plato mission. You can say that Plato is essentially like a Kepler mission, but it has not one mirror, it has 26 mirrors, and has a much larger field of view than Kepler. So everybody is very, very excited and waiting for this mission, because it will, again, we are hoping it will again transform the field. Then Ariel, I will come back a bit to Ariel. This mission will observe planet atmospheres. And will come back to why that is important. So, what was so great with Kepler? How did it transform the field? Well, Kepler found out that there are planets everywhere. Planets are everywhere. Every star has at least one planet. And many look completely different from what we know and what we are used to. Even our closest star, Proxima Cen, has at least, I actually changed this just last week. I was about to write, I did this presentation a few weeks ago, and then I wrote one planet. But last week I was at a conference and they had detected another one, so now we have 2 planets around our closest star. Should we be afraid? No, don't be. So now, the first exoplanet was detected 30 years ago. Today, almost 6,000. The most unexpected discovery was not that planets exist, that every star has planets, but the diversity of exoplanets, which started with the first detection. I mean, this so-called hot Jupiter, a Jupiter-like planet extremely close to the host star. There are planets that are so close to the stars that through tidal forces, they are completely deformed. Look, they are not even spherical anymore. If the planets are smaller and so close to the star, their entire atmosphere can be blown away from the solar radiation. If they are very close, there will be, and small, there can be lava planets. There can be there are planets that have a rain of lava. There can be very puffy planets as well, with densities so low that it's much, much lower density than water. There are planets, if you remember, I told you that, maybe I forgot to say it, but all the planets in our solar system orbits the sun in the same plane, in the same direction and in the same plane, because they formed in this gas disk, which is rather flat. But there are planets that have extremely different orbits. They can orbit backwards around the star. They can move in polar orbits. And this requires enormous forces to change their orbits in such a way. There are planets orbiting 2 stars. I'm sure you have seen Star Wars. And it's true. That was before the first exoplanet was detected. The first movie came out in 1977. But George Lucas was right. There are planets that orbit 2 stars. as this one, Kepler 45. Up, up, up. And we have also very, very strange, peculiar planet systems. So, for instance, this one here, you have TRAPPIST-1 with 7 planets. And this star, TRAPPIST-1, is very, very small. Is about the same size as Jupiter. And it hosts at least 7 planets. They are very small, like Earth, or even smaller. And their orbital periods is, the innermost has 1 year for that planet is 1.5 day. The next one is 2.4 days. Next one is 4 days, 6 days, 9 days, 12 days, and almost 19 days. You will see planets everywhere. And it was a huge surprise that the most common types of planets do not exist in our own planet system. So the question is, maybe not what we found, but we have not found. Why have we found the most common types of planets in our own planet system? Why do our planet system look like it is? We still don't know this. But the most common types of planets are planets smaller than Neptune, up to 3 or 4 times larger than the Earth. And if they are a little more massive, a little more larger than Earth, they are called super-Earths. And then a little more massive and larger than that is called mini-Neptunes. So these 2 types of planets are the most common types of planets, but not in our system. So here I show a few graphs. So just to show all the variety of the planets. So we cannot just say that we have detected, if you see a press release, now we have detected the most Earth-like planet so far. But then they're often talking just about size or mass or something like that. But if you see these graphs here, on the left one has plots masses as a function of orbital period around the star. And the right one plots the radii of the planets versus orbital periods. So this one, the right one, has observations from the transit method and the left from the radial velocity method. And as you see here, almost 4,000 planets here and 1,600,000 planets with measured masses. And so almost 6,000 planets. But as you see, there are some, they are not just randomly scattered in these plots, right? So there are planets here that are called hot Jupiters in both plots. We see them, they have very short orbital periods. Look here again. This is logarithmic scale, this is 1 day. So look here again, 1 day. There are planets with orbital periods, a year, less than 1 day. Actually, the record is 6.7 hours. It's amazing. Anyway, so you see these hot Jupiters with both methods. And here I've put in our solar system planet, and you see it's very, very empty here. Earth is here. No Earth-like planet is detected yet. We also see cold Jupiters, where are at distances Jupiter-like planets at about the same distance as our Jupiter has. But they are mainly detected with the radial velocity method and not with the transit method, because the geometric probability is so small to detect planets further out with that method. And we also see a lot of these super-Earths and mini-Neptunes here. A lot of them we see with the transit method. Not so many, we see them, but not as many with the radial velocity method, because it's very difficult to search for small planets with that method. So we cannot just use one method, we need to have many methods to be able to search for all types of planets at all types of distances from their host star. So, no Earth-like planet or system like our own has been discovered yet. But does this mean that the Earth and our planet system are unique? What do you think? Are we unique, given these figures? Well, they look pretty unique, right? But but the observed populations are not the same as the true populations because of these difficulties that the method has to detect the planets at different distances from their host star. So, for instance, hot Jupiter, this looks like there is a lot of hot Jupiters. Here in the transit method, we see no cold Jupiters. We see only a lot of hot Jupiters. But actually, as the first planet was, actually, it's just 1 in 100 stars that has a hot Jupiter. We don't have it, but it's not so many that has. Small planets, on the other hand, sub-Neptune, super-Earths, they exist at least around half of all the stars. And small stars have also fewer gas giants and more small planets. So, even though we haven't discovered an Earth yet, there may be many Earth-like planets waiting to be discovered. But we need new instruments, new methods, not just new instruments, but also other methods to detect these other planets. Oops. It's not really. Oh. Okay, here. I wanted to show you this. So this is 1,800 planets in 726 planet systems detected with Kepler. And you see here is the orbits of the 4 innermost solar. Here is Earth. It compares how large the systems are, how close in the planets are to the host star. So look, all these planets fits within our solar system. And you see also the sizes are relatively sizes here, Jupiter to Mercury, and also the colors. The red one is very hot planets, can be more than 1,000 degrees, and the blue are cold planets. But you see, the systems that we have detected so far look completely different from our own. So why do we care about how the planet system looks like, the architecture of the planet systems? Do we care? Why is it important? Well, the architecture likely plays a very important role in planet formation, especially for rocky, habitable planets. Imagine you have a large Jupiter that forms far out in the system, and then it moves towards the star. That will stop small Earth-like planets at the right distance from its star to form. So in those systems, there will likely be no habitable planets. And gas giants also dominate the long-term stability. And Jupiter, in our own system, likely protects Earth and the inner system from a lot of asteroids and comets. But if we talk a bit more about life. So life on other planets, even if it's carbon-based and needs water, etc., everything that we have, but if it exists on other planets, it can look very, very different anyway, because there are many different conditions compared to Earth. For instance, Kepler-16. This is NASA that made an exoplanet travel bureau. They've made posters. So if you want to go to buy a trip somewhere, you can go to this travel bureau. Do you want to travel to Kepler-16b? Relax on Kepler-16b, where your shadow always has company. So, I mean, what if we were orbiting 2 stars? We would always have 2 shadows. Or Planet Hop from TRAPPIST-1e. That it was that system with 7 planets very, very close. You can hop between planets. And so even if it's carbon-based life, what if the planet orbits around a much smaller star than our sun? Small stars are much redder. There are few photons that the photosynthesis use. So the photosynthesis that is crucial for life on Earth would have been a much harder time to work on such planets around those stars. So there on those stars, stars are red. So on those stars, you can maybe, where the grass is always redder on the other side, you can have red grass. So how do we define habitability? Well, it's not easy. Maybe we have already found life, maybe we're already looking at it, but we don't understand what it is. But we have to start somewhere. Anyway, so life don't have to be on the surface of a planet, right? It can be beneath the surface. For instance, on Earth, we have these hydrothermal vents. That is life without sunlight. They form in places where seawater meets magma on Earth. And there, organisms convert heat, methane, and sulfur compounds from black smokers into energy. So look at this cartoon. Meanwhile, at the bottom of the ocean. Do you think life exists at the surface of the ocean? Nah, there are no hydrothermal vents up there. What would they use for energy? True. So what if we are as ignorant as the organisms in this cartoon? Maybe we can't even have the imagination to, imagine how life could look. But we have to start somewhere. So if we consider carbon-based life as we know it on the surface of rocky planets, there are a number of requirements. We have to have, as I said, a source of energy. We need liquid surface water. We need dry land. We need significant supplies of basic elements of life. Carbon, nitrogen, oxygen, phosphorus, sulfur. And we need water not only for development of our molecules, but also for the development of plate tectonics, which may have been critical for the development of life. We need a climate regulation as on Earth, or through the carbon dioxide cycle. We don't want the carbon dioxide, all of it, in the atmospheres, as you know, because it increases the temperature. As on Venus, the temperature there is so high that lead is melting, because all is carbon dioxide in its atmosphere. Whereas here on Earth, water washes away carbon dioxide, so it goes through down in the ocean and in the interior. So with those requirements for life, we need a stable energy source, over billions of years. Likely orbiting a solar-like star. There are many different types of stars. Some live very short, have lifetimes much shorter than that, while some live much longer than the sun, but they may not be stable. We need a rocky planet that is not too small, because if it's too small, like Mars, it's a rocky planet, and Mercury, rocky planets, but they're so small so they cannot hold on to an atmosphere. It can't be too big, because then it will attract a lot of gas and become a Neptune or gas giants. We don't want that either. We need it to be geologically active, and we need it to be stable, have a stable climate and orbit. And there are many, many, many more requirements. It's actually very, very hard to produce a perfect habitable planet as the Earth. And if we look at the stars, it's not just a planet. It has to orbit a good star. So, Earth is a stable star, lives for 10 billion years. But even though it's very inactive and stable, it still sometimes look like this. I'm sure you heard about coronal mass ejections or solar storms that can affect us here on Earth. So what if stars were even more active than our sun and you were very, very close to the star? Well, not good for life. So, we're looking for solar-like stars. I mean, our star has allowed a remarkable level of stability. So Earth has been habitable almost from the start. But complex life on Earth took billions of years to evolve. Note also that the conditions were completely different than today. So how common is the sun then? Well, if we have a look at this figure, the most nearby stars we have. So here you see to the left here you have the hottest, most massive, largest stars with short lifetimes, and then to the right you have smaller and smaller stars. And as you can see, small stars are much more abundant than large stars, and they also live longer. Our star is a G star, it's here. But the most common types of stars are M stars. They are 10 times as common as the sun, But they're not good for habitability because they are much more magnetic active, and they have a lot of these solar storms, etc. So, how common is the solar system then? I mean, our type of star and our solar planet system and Earth. Well, if we don't know yet. We don't know yet, but if you make an order of estimate with the facts that we have today, let's see, if another civilization should look for 10, 20 years at our solar system, this is what they would detect. They would detect the sun, and they would detect Jupiter. That's all they would see, if they had our technology that we have today. That's all they would see. So that's also the same that we see in other planet systems. And from that, in other systems, we are trying to deduce how frequent Earth is. And it's hard. But let's give it a try. 10% of the stars are solar-like stars, and we want that. 10% of the solar-like stars have Jupiter-like planets, and 10% of those Jupiters and systems have Jupiter-like orbits. And then 50%, about half of all the stars, have larger planets, super Earths, mini Neptunes, hot Jupiters, very close to the star. And in those systems, there are likely no habitable planets because they wouldn't be able to form. So, about 1 in 2,000 stars, 1 in 2,000 of all stars in our galactic neighborhood is a Sun-Jupiter system that could potentially have Earth-like habitable planets. And that's a pretty big number, right? Because we have hundreds of billions of stars in our galaxy. But we don't know. Oops. This is not, I'm too far away, I think. Maybe I should stand here. Anyway, so what we want is a planet in the so-called habitable zone. And that is the distance from the star where water can be liquid. So it requires the right temperature. And the habitable zone, the distance and the width of the habitable zone, it changes with the type of star. You have to be further out if the star is hot, and very, very close to the star if it's small. But note that being in the habitable zone does not guarantee habitability. You have, for instance, to have an atmosphere, etc., etc. So let's say that we have done everything. We have detected a lot of planets. Maybe we have shown that there are Earth-like habitable planets everywhere in the galaxy, or at least here and there. But how do we detect life on them if we don't want to go there? Suggestions? How do we do? Yes. He said the atmosphere. Yes, that's one of the things. So again, this is the pale blue dot. Here you see it. Better than any picture we have on an exoplanet. But in order to detect life on another planets, we must remember that life must be present for a long time, for gigayears, because otherwise we wouldn't be able to have time to, it will die out before we will have time to detect it, given the large number of stars. And this is why we also don't consider life beneath the surface of a planet. We will never be able to detect that remotely, right? There can be life below the surface on every planet. We will never see it unless we go there. Maybe not even then. We're not even sure if there, anyway, have been war. We are still arguing about the detections on Mars and Venus. Anyway, so they must leave a global and remotely detectable signature, and they can do that in 3 ways. One is that they can send radio signals. So we are doing it constantly. Radio signals is pouring out from Earth in all directions. So we could listen for radio signals that seems to be sent out by an intelligent civilization. But it's very hard to know if it's from a civilization or if it's just physical. And people are doing this in the SETI project, but they haven't found anything yet. You can also observe something called technosignatures from a civilization. That is, an intelligent civilization must have built something that is large enough for us to detect. I will come back to this. And we can also observe the atmosphere, and we call this biosignatures of the gases. And this builds upon the fact that life changes the atmosphere. From on Earth here, in the beginning, the atmosphere here, we did not have any oxygen at all. But life has produced oxygen. So this is the base of that method. But note that if we would detect that, such a signature, it doesn't mean that life has to be intelligent. I mean, if someone looked at us for 1 million years ago, 500 million years ago, there would have been life here, right? But not intelligent life. But this one, the last one, is the method that almost everybody are using. But I just want to show to you anyway, this technosignature way to detect intelligent civilization. I was actually in the committee for a PhD student in Uppsala, Sweden, last fall, that spent 5 years of his life to search for so-called Dyson spheres around other stars in the Milky Way. He didn't find anything, but at least he could have put upper limits to how many there could be. This Dyson spheres is an example of a technosignature, and it is a hypothetical megastructure around a star that captures a large portion of the star's radiation. That is like a solar panels. You build huge solar panels around the star to capture the energy. Like if we would take Mercury, we can use Mercury to build huge solar panels around our sun. But if we would detect something like that, it doesn't mean that the civilization is still there, right? They could have died. But anyway, biomarkers, remote signs of life, are the most common way to search, investigate if there is possible life or if the planet is habitable. So it builds upon spectroscopy. You get, it's like molecular fingerprint spectroscopy. So what you would like is to have is this. We cannot get this yet. This is real spectra from Earth, Venus, and Mars. So what you see here in Mars spectrum is only a signal from carbon dioxide in infrared wavelengths. You see Venus here in yellow. You see carbon dioxide and carbon dioxide. Yes, that's all. But then you see Earth here in blue. You see signatures from water, N2O, CO2, O3, ozone, H2O, methane. So this is the hypothesis that life can be detected by combined signatures of oxygen, water, carbon dioxide, and methane. But it might not be true, because there could be potential ways to produce these species in the right, that fits to the observations without life. But normally they shouldn't, for instance, oxygen should not be able to persist for a long time in an atmosphere. It will completely vanish after some time. So that is what we want. So observations of atmosphere is currently done by James Webb Space Telescope. So here we see wiggles here in the spectrum, the light from a star. And these wiggles here, I can't see. Here we have carbon dioxide. Here we have methane, carbon dioxide. That is very, yeah. Anyway, so the method by which this is done is in using the transit method. When this planet is transiting in front of the star, some of the star's light will pass through the planet's atmosphere. And at those particular wavelengths, if this atmosphere have, for instance, methane in it, at that particular frequency or wavelength where methane can absorb starlight, the planet will suddenly look bigger. while at other wavelengths it will look smaller. So this is actually just a measure of the size of the planet. Size gets larger when you have a molecule at that particular wavelength. So this is exactly the same as a transit, but in transit photometry we measure the entire white light. But here we measure a transit in many different wavelengths. And the Ariel space mission will do the same. And it's dedicated to do only this. James Webb only does this for a small part of his mission. So Ariel has a planned launch in 2029. But the thing is that these measurements are only made towards transiting planets. And there are very few planets that are transiting. And most transiting planets are also very close orbits. And this method is also very... it's hard to detect small atmospheres from small planets like the Earth. So what we would like to have is a direct approach. Like this slide, we would like to observe the planets directly, not via the background star from the background light from the star. We want to look at them directly without the star and see the emission that is coming directly from the planet. But this is unfortunately much too difficult for our current technology. But we can do direct imaging of exoplanets. There have been a few planets that there are actual pictures of this. These small dots are actually planets. It's like the pale blue dot, but these planets are up to 10 times more massive than Jupiter. So this is not small planets we're talking about. Really, really large planets, almost like small stars. And they're also very far away from the stars. Because if you remember, I said that the light from the stars is 1 billion times brighter than the light from the planets. So you have to block out. Here they have blocked out the light from the star. And if the planets are too close to the star, the light will be blocked away. You will block out the light from the planets as well. But what we like to do is new missions, of course, that can detect small planets with imaging and take spectroscopy of their atmospheres. And there are new missions that is in their pre-formulation phase. So, for instance, this one, the Habitable World Observatory, with very large mirror like the James Webb. Launch date, 40s, maybe in the 50s, 2040, something like that. And what this mission will do, let me start from the beginning, is that it will have a shield that will block out the light from the star. A really big one. It's like 100 meters across. You will have a space telescope, and then you will place this star shade just in front of the star. You have to be really, really, really precise because the planets are very close to the star. So in this way, we may actually have real pictures of Earth-like planets, small planets, and we may get spectroscopy, direct measurements of their atmospheres in like 20 years from now, 20, 30 years from now. There are other missions like, well, we could have the same star shield, like halfway to the moon or so, 100 in diameter, but we can use one of the new big, very, very extremely large telescopes, like 30, 40 meters that are being built on ground right now. Because the advantage is you will have a much, much larger mirror, can collect more photons. And if you already know where to point, etc., you're not as dependent that you need to have continuous observations as with transit method. So this is also something that is planned, the hybrid observatory for Earth-like exoplanets. Or you can have something like this, the large interferometer for exoplanets called LIFE. This is a European project. These two are NASA projects or potential projects. They have not been decided on yet. So here you have a fleet, several space observatories that are flying in a formation. Several spacecraft flying in a formation, and with using a technique called interferometry to like virtually block out the signal, the light from the host star. So they don't need a solar screen like this. So this is very, very exciting, and many people are working to make these projects happen, but it will take many, many years. Maybe a few of you young people will be around when they come up and will be launched. And then it takes a number of years to do the observations. So it takes some time. Maybe like 40, 50 years from now, we will know. So we can also look at this question, if there's life, from another perspective. We can ask ourselves, if our Milky Way, we know that our Milky Way is 12 billion years old. Life here on Earth evolved for a few billion years ago, but there should have been many, many more places or planets where life evolved for a long time ago. And they would have plenty of time to even colonize the entire Milky Way. They would. Why aren't they here? Where are they? It's a valid question. So here, the Drake equation tries to compute the number of technologically advanced civilizations in the galaxy. I mean, maybe are we alone? Or are there many intelligent civilizations? But if that is the case, why aren't they here? So it depends on a number of things, how many stars, how many planets, etc., evolution. But we have come here, we have fixed these parameters. We are here now. The next missions will take us here. But then we have more like we leave for the biologists, the geologists, psychologists, the length of the civilization. We don't know that. We leave that for for you guys maybe, to explore. There's also something called the great filter, or the final exam, which is a theory that says that there is at least one or several hurdles that are so high, so difficult, that no species can clear it and move on. This will wipe out civilizations before they can encounter each other and colonize the galaxy. And it can be anything from the origin of life, step from single to multicellular life, step to intelligent life, step to technological civilization, and then we have a long list of nuclear warfare, pathogens, pandemics, artificial AI, meteorite impacts, supernova, blah, 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 blah. There are many things that could happen that can be this final exam. We have actually Earth has had at least 5 mass extinctions the past 500 million years, when like up to 95 of all the species have died out. From supercontinent formation, impacts, flood basalt eruptions, global glaciation, and global warming. But if this great filter, the final exam, exists, if it does, if this is the answer to why it's so quiet, why they are not here yet, the question is, what about us? Have we passed it? Did we get approved? Or is it in front of us? Are we one of these civilizations that won't? I mean, maybe we have passed several difficulties here. We have gone from life have evolved, single cells to multi-cells to intelligent, technological, but then something happens here that is really, really hard to overcome, and we will become extinct. We don't know. But our apparent aloneness in the universe may be a good sign, because that would indicate that we safely made it through this bottleneck. And that is us that will colonize the Milky Way. So, summary of this talk. If you remember anything from today, remember that our planets, the architecture of our planet system, and even our sun, is not the general rule. Most planets do not look like this. Most systems do not like this. Most stars don't look like our sun. But perhaps it is our imagination that limits what we think life look like and what its requirements for habitable planets are. What if life can be as extremely diverse as exoplanets has turned out to be? I mean, we started with the assumption that all planets, Earth and all planet system would look exactly like our own, right? But they don't. They are extremely different. So maybe it's the same thing with life. Maybe we have even discovered it, but we haven't even understood that it's life. And I want to end this talk by another quote by Carl Sagan. We arranged a global civilization in which the most crucial elements profoundly depend on science and technology. But we have also arranged things so that almost no one understands science and technology. This is a prescription for disaster. This might be one of these final exam things. We might get away with this for a while, but sooner or later, this combustible mixture of ignorance and power is going to blow up in our faces. This is true, and this is worrying. This is not a good mixture, ignorance and power. So that's all for me. Thank you, and I will take questions. So, if you have any questions, feel free to ask them now, or you can wait around until afterwards and ask me questions in private. Anyone?
Thank you for exciting lecture, and maybe depressing if you come to final conclusion that we are alone in this universe.
Have the mic very close. Very close.
Yeah. So depressing conclusion that we might be alone in the universe.
We might. We don't know.
We don't know. But for me, it's interesting how you define life, because we are based on our system that defines life. But there may be different types of life based on different components, different organizations. So are we prepared to see this? Do we know?
There have been many investigations, for instance, if life is maybe silicon-based instead of carbon-based. Or they could use, instead of water, they can use liquid methane. As we all know, maybe, we have liquid methane lakes on the largest moon of Saturn, Titan. There are liquid methane lakes. But in every investigation that has been done so far, it always turns out that carbon is absolutely the best element that can produce most molecules and complex molecules, and water is also phenomenal as a liquid and solvent, enabling production of large molecules. People here might know this better than me, biologists, etc. But still, we are of course investigating, but it's also very hard, as I said, we try to have everything open, but it's hard to detect. As I said, we have to have remotely detectable signatures from a civilization. For instance, they could be below the surfaces. We can never detect it. So what we do, we are starting with things we know and take it step by step. So right now, that's why we are so focused on trying to detect rocky planets that are in the habitable zone. So that's like the first step. But so far we have not, but we have detected a lot of other planets, of course, around a lot of different types of stars, because they are much easier to detect. But so far we have not been able to even search for Earth-like planets in the habitable zone around solar-type stars. And Plato will actually be the first mission that will be able to do this. And Plato will be launched end of next year. So, invite me again in 10 years' time. Maybe I have completely new, because in 10 years' time, we at least might know if Earth is common or rare. Just that is a huge step forward. Yep.
Thank you very much for reminding us that we are not the center of the universe, and that life might look different to what we are viewing ourselves upon. But could you say something about what kind of science projects and countries which are working with this field, and how collaboration is happening, how data is shared, and in a way how the whole setup is of the science around it?
It's different from, for instance, we have ground-based observatories with instruments that do these radio velocity measurements. Then you apply for time. So I'm working with an international team of researchers, and we apply for time twice a year. Every year we apply for time. We write, we want to observe these and these planets, and we want to do this and this. And we compete with researchers all over the world. And then sometimes we get time, sometimes we don't. But these space missions are a bit different. Some of these missions have completely open data. For instance, the TESS mission that is working right now. All of you can go down and download the data from the TESS mission right now. And a lot of data, also from these ground-based observatories. When you get the data, you have applied for data, you get the data. You have 1 year that the data only belongs to you and your team. But after 1 year, it's open. But some of these space missions, the data is open immediately. So you can go down. I actually have an exoplanet course for my students in Gothenburg. And as one of the projects they do, is download data from either Kepler or the TESS mission, and then they search for planets in this transit data. And then they compute how large they are, etc., etc. So, but some missions are, you have built a mission, you have paid for it, it's closed, no one else can use it, but it's different. But these super large missions, they are often open. If not immediately, then after 1 year is open.
I haven't really thought it through yet, but there's something about, like, I can't even wait for food to cook. How do you kind of, is there a talk about how we meet the challenge of like multi-generational focus, or like we're talking about like 2050, 2070,
yeah. Mm-hmm.
And because there's like a lot of people, we can talk to people who were born before power came to their cities, and now we've come so far, but how do we keep the focus? And like, it seems like we need to watch for a really, really, really long time to figure out the hard things.
I don't have a good answer. It's very exhausting, also as a researcher. As I said, I'm actually working on an article right now. We have observed the planet system for 5 years. We have discovered 2 planets. It's combined test data and radio velocity measurements from ground. We have observed it in these ground-based observations we have performed during 5 years. We have found 2 planets and possibly a third one with an orbital period of 5 years. But that star is active. So the star has activity at the same orbital period as the third planet. Maybe. We don't know. We probably need to observe 5 or 10 more years before we can say, this is stellar activity or this is a third planet. So now I'm not waiting anymore. I will publish the paper, say we have 2 planets and maybe a third one. So we have to wait. So this is very exhausting because we researchers, we get our grants, we need to publish papers. We can't wait forever. So our system is not built for this. We have a bad system that promotes scientists. We would need our whole lives, to do this. That's why ESA and NASA, they want, if you are going to start to work at these agencies, they want young people to lead the projects because it might take 10, 20, 30 years before launch, and then you need a number of years to do the observations, and then, yeah.
I had a question about the beginning of the presentation. You're talking about velocity radiation to measure the mass of planets.
Yeah.
And if you look just at one big Jupiter-like planet, you can, I think, differentiate the way the orbit of the sun or the star changes. But how do you differentiate planets? Because you said you could measure it for Earth and Jupiter.
The amplitude is lower for small planets. So it's the amplitude of the signal that gets lower with small signals, with small planets.
All right, and you can differentiate, like, I imagine that the sun only has one major elliptical.
let me show you. I just showed a few very nice figures. Let me show you this figure. I showed you the transit method. I showed you deep transits, right? That was from a big planet, very bright star. Look at this here. Here we actually have transits from 2 planets. You don't even see the transits by eye. So we have to develop specific transit detection algorithms that wash out periodic data in the noise. And this is transit data, but it is even worse in radio velocity measurements. So what we do is we measure the radio velocity of the star now, and then maybe 2 hours later, maybe next day, maybe next month, etc. as a function of time. And you get this is radio velocity. Every dot here is radio velocity measured as a function of time. And this does not look periodic at all. How do we? Actually, this system has 2 planets and a very, very active star. But how can we know? I mean, you have, so these are 2 planets, and this star is this here is the model as the star. I mean, so it can be extremely difficult. There are a number of occasions where people have announced that, we have detected a planet. And then a few years later, no, it wasn't a planet. It was an active star. Or you can miss in all this activity. There can be many more planets in the system that we can't see because the star varies so much in itself. Yeah, so I just showed you the good stuff. This is the reality, what we are struggling with every day.
And could I ask you one more question?
Yeah.
Because you're talking multiple times about rocky planets, and that life is most likely on rocky planets, and also probably the environmental conditions will be right. But isn't there a chance that life would exist on more ice giants or other types of planets?
Of course, there could be, things that we can't even imagine. There was actually a detection of, a few years ago, there was a detection of a molecule that was believed only to be produced by life in the atmosphere of Venus. So at that time, it was hypothesized that there could be life in the atmosphere 50 kilometers above the ground in Venus. But no, it turned out that no, there wasn't these molecules. It was a mistake. They didn't even detect that molecules. But there are maybe, of course, be life floating around in the atmospheres of planets, but that's not, we don't think it's likely, or at least the problem is that you can think of so many things. It can be this. It's an endless, you can think of whatever you want, right? But we have to back it up scientifically somehow, that we prove that this, if we assume this and this and this, it is likely that life can be here on this type of planet. But, you can't just assume anything. It has to be, based on some evidence or something.
Okay. It seems to me, it hears to me, that the uniqueness of our planet has not diminished over time. You have found so many other things that says that if there is something out there, it's different.
Yeah, it hasn't diminished.
Yeah.
Opposite.
Yeah.
We are more and more, appreciating the uniqueness of Earth. I mean, there might be lots of Earth-like planets. Again, invite me in 10 years' time, we may know from Plato. But even though we are not unique, we have found out that there are so many different types of planets around so many different stars. So what we do know is that Earth-like planets in our system does not exist around every star. That we know for sure already.
So take care of this one. Huh? Take care of this one. And Carina, thank you very much for a very exciting, interesting talk. Of course, when you come to Bergen, you don't know it, but you always need an umbrella. And since you didn't bring one, I'll give you one. Thank you very much.
Thank you.
And
wants to have questions for me privately?
you can come if somebody wants to talk more, it's possible. I will just say that there is going to be a Darwin Day lecture around this time next year. due to the 365 days of the Earth's rotation and Darwin being born on the 12th of February. There is going to be Horizon series lectures several times this year. The first is likely some depressing things about the climate, but it's not for sure. But it's quite sure that it's depressing, isn't it? Yeah. So thank you so much for coming. If you have questions to Carina, please come forward, and see you next time.
Jeg satt og tenkte at det er så mye nytt du presenterer også, det er vanskelig å...
Du er veldig flink. Har noen sagt det til deg? Du er veldig flink. Har noen... Clever.
Ja, var dere god...
Aktiv, mener du?
Nei.